So today we are going to see what is called state space representation. Up to now, we had seen how systems can be modeled with the help of transfer functions. What is transfer function? Ratio of Laplace transform of output to Laplace transform of the input when all initial conditions were zero. But it had its own limitations. For example, the system had to be time invariant system. The system had to be linear. The no, initial conditions should have been zero, right? But practically, systems are non-linear. There may be time varying parameters. There may be some non-zero initial conditions. The system can have many inputs and many outputs, or it may be a MIMO system, multi-input, multi-output system, and so on. So transfer function cannot be used effectively to represent these kind of systems. So we need to go for a more general way of modeling systems. State space approach is one such system. So we are going to look into the details of state space modeling in this lecture. So state space representation. State space representation. The basic idea of state space representation is that an nth order differential equation can be broken down into n first order differential equations. Okay, that's what we are doing actually happening when we are representing a system in state space form. Let us take one example, then it will be more clear. So here I have two masses. This is M2, this is M1. Okay, there's a spring, there's a damper, another spring, another damper. To mass M1, a force is being applied, U of t. Okay, so this spring constant is K2, this is K1, this is B2, this is B1, and this mean displacement is Q of t, and the mean displacement of M1 is P of t. Okay. So suppose P of t is the output variable. Okay, so we know how to obtain this in transfer function form. So if you do in transfer function form, what you get, we know there are two masses. So the corresponding matrix will be of the order 2 by 2. Okay, so what will be the elements correspond to mass M1? What are the elements? S square M1, straight away in Laplace domain I will write, plus SB1 plus K1. Okay, so 1, 2 element and 2, 1 element will be always negative. So minus of K1 plus SB1. Minus of K1 plus SB1. What is the 2, 2 element? S square M2 plus S into B1 plus B2 plus K1 plus K2. Into what? Into Q of S, P of S. Sorry, into P of S, Q of S. P of S, Q of S. Okay, must be equal to what? Must be equal to U of S 0. The force applied. Okay, M1 has an external applied force of U of t. So Laplace transform of corresponding term will be U of S. There are no external applied forces on mass M2, which means it is 0. Okay, then it is easy to find the transfer function. Either output variable P of S by U of S can be found. Okay, and so on. So in state space form, it is different. Okay, so what are the differential equations here? First, let me write once again the differential equations pertaining mass M1. Okay, so for mass M1, you will see that the applied force must be equal to what? Sum of the internal forces. So U of t must be what? M1 P double dot t. What do you mean by P double dot t? P double dot t means d square P by dt square. That's the meaning. Okay, P triple dot t means d cube by dt cube of P of t. That's the meaning, standard notation. Okay, so I can write M1 P double dot t plus K1 into P minus Q plus B1 into P dot t minus Q dot t. Okay, or from here I will get P double dot T as what? 1 by M1 into what? U of T minus K1 into P of T minus Q of T minus B1 into P dot T minus Q dot T. Okay, P dot T minus Q dot T. This is equation 1. Now, coming to mass M2. Mass M2, we don't have any external applied force. So 0. 0 equal to what? M2 Q double dot T plus K2 Q of T plus B2 Q dot T plus K1 Q of T minus P of T plus B1 into Q dot T minus P dot T. Okay, or if I am taking Q double dot T term to the left side. Okay, so what will I get? I will get 1 by M2 into what? 1 by M2 into what? Minus K2 Q of T minus B2 Q dot T minus K1 into Q of T minus P of T minus B1 into Q dot T minus P dot T. This is 2. Okay. Now what I will do is that I will define a set of variables. Okay. Let me define the set of variables like this. Let P of T equals x1 of T. Okay. x1 of T is the newly introduced variable. That is called state variable. Okay. P of T is x1 of T. So what will be P dot T? That is x1 dot T. I will call that as another new state variable x2 of T. So what will be P double dot T? P double dot T will be x2 dot T. Okay. I will not call this as x3. Okay. Why? Because state variables are those variables which we need, the minimum set of variables that we need to describe the future of the system. Okay. Given the input signal. Okay. With the help of the input signal, we should be able to predict how the system will be behaving in future. Okay. So state variables are the minimum number of variables which can completely describe the dynamic behavior of the system. Okay. Given the input at that instant. Okay. So P double dot T is x2 dot T. So this equation is up to P, order is P double dot. Okay. So I have defined P double dot as x2 dot. Now, let me define Q of T as x3. Q of T is x3 of T. So what will be Q dot T? Q dot T will be x3 dot T. Okay. And that is nothing but x4 of T. So up to what point I have to go? Up to Q double dot T. So what will be Q double dot T? Q double dot T will be x4 dot T. So now I can rearrange equations 1 and 2, rewrite equations 1 and 2 in terms of these state variables. Okay. So P double dot T will become what? X2 dot T. So equation 1 will imply X2 dot T equal to what? U of T by M1 minus K1 by M1 into P of T minus Q of T. P of T is x1, Q of T is x3. So x1 of T minus x3 of T minus B1 by M1 into what? P dot minus Q dot. P dot is x2, Q dot is x4. So x2 of T minus x4 of T. Okay, this is equation A. Similarly, equation 2 will imply what? What was equation 2? Q double dot T. Q double dot is x4 dot. So x4 dot T equal to what? Minus K2 by M2 into Q of T. Q of T is x3 of T. x3 of T minus B2 by M2 into Q dot. Q dot is x4 of T. Minus K1 by M2 into Q of T minus P of T. Q of T is x3 of T and P of T is x1 of T. So I can write x3 of T minus x1 of T. Okay. Minus B1 by M2 into what? Q dot minus P dot. Q dot is x4 and this is P dot is x2. Okay. So I can write x4 minus x2. x4 minus x2. Okay, this equation B. Now these can be written in matrix form. Okay, so you see what is happening. I can write. Let me write all these things together. X1 dot t is equal to what? How do we define x1 dot t? We have defined x1 dot t as x2. So I can write this as x2. Okay, so x1 dot t is x2. Okay, now what is x2 dot t? X2 dot t is this expression. Okay, we have already seen this is x2 dot t. Okay, so what will you get? That will be what? Minus k1 by m1 into x1t minus x3t minus b1 by m1 into x2t minus x4t plus u of t by m1. Okay, now what is x3 dot? X3 dot t is x4 of t, is it not? X3 dot t was x4 of t. So I can write x3 dot as x4 of t. And finally, I have x4 dot t as what? Like this. Okay, so minus k2 by m2 into x3 of t minus b2 by m2 x4 of t minus k1 by m2 into x3 of t minus x1 of t minus b1 by m2 into x4 of t minus x2 of t. Okay, so now all these things can be expressed in a matrix form. Fine. How? For example, like this. So here I can write x1 dot t, x2 dot t, x3 dot t, and finally x4 dot t. Okay, must be equal to what? Some matrix into x1, x2, x3, x4 plus something into u of t. Okay, so what is x1 dot? X1 dot is x2. So that means 0, 1, 0, 0, 0. Okay, x1 dot is x2. Expand is 0 into x1 plus 1 into x2 plus 0. So x1 dot is x2. What is x2 dot? So minus k1 by m1. Then x1 term we have picked up only minus k1 by m1, right? So minus k1 by m1, correct? And what is x2 term? X2 term corresponds to minus b1 by m1. b1 by m1. X3 term is k1 by m1. And x4 term is b1 by m1. Okay, so plus 1 by m1 into u. So I have 1 by m1. Okay, now what is x3 dot? X3 dot is x4. That means 0, 0, 0, 1, 0. What will be x4 dot? It will be k1 by m2. Okay, k1 by m2. Then next term will be b1 by m2. From this equation, okay, from x4 dot equation, I can pick up the coefficients. Minus k1 minus k2 by m2 and minus b1 minus b2 divided by m2. Okay, and if P of t is given as the output variable. Okay, what was P of t here? P of t was x of t. So I can write my output y of t as 1, 0, 0, 0 into what? x1, x2, x3, x4 plus something into u, 0 into u. Okay, so you see here, what was the order of the original system? It was fourth order. So the fourth order system has been broken down into 4 first order equations. Okay, 4 first order equations. Right? This is the basic idea behind the state space representation. And nth order differential equation can be broken down into n number of first order equations. Okay, so this way of representation is called state space form. So in general, there's a standard form. The standard form is x dot t. What is this? What does this bar represent? It represents x dot is a vector. Okay, x1 dot, x2 dot, etc. up to xn dot. Right? X dot t equals a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. Okay, so what is a here? A is this matrix A. What is b here? B is this column vector. What is C here? C is this row vector. And what is D? D is this null vector. Okay. Why B is a column vector? Why not? Why B is not an array or a matrix? Because we are dealing with SISO systems. Okay. Single input, single output. If there were more than one input, then your B matrix would have been an array or a matrix of appropriate dimension. Similarly, if you had more than one outputs, your C matrix would have been an array. M rows and N columns would have been there. Okay. So since we are dealing with SISO, single input, single output transfer functions, your B is a column vector and C is a row vector. Okay. So this is what is called states. Okay. So let us define state variable more formally. What's the state? State of a system. State of a system is the minimum number of variables. The minimum number of variables which can completely determine the dynamic behavior of the system. The dynamic behavior of the system. The dynamic behavior of the system. For any time t greater than or equal to t naught, given the input r of t. Okay, so if you are given the input signal, along with the input signal, state variables, they are the minimum number of variables which can completely describe the dynamic behavior of the system. Okay, so you see what was our x1, x2, x3 here. X1 was the displacement of mass m1. Okay, and x2 was the linear velocity corresponding to mass m1. Okay, similarly x3 was the displacement of mass m2, and x4 was the linear velocity corresponding to mass m2. Okay, so you can completely describe the dynamic behavior of the system if you are given the input function. Okay, that is what is state variable. Fine. Now, state variables or state space form can be obtained from transfer function as well. Okay, or you can convert a transfer function into state space form. So we will see both. Okay, so first one is converting state space to transfer function form. Converting state space to transfer function form. Converting state space to transfer function. Transfer function. Okay, you are given the equation x dot equal to ax plus b, or you are given the system matrices a, b, c, d. Okay, how can we obtain the transfer function? Okay, so what's the state space representation? X dot t equals ax plus b. Okay, and y equals cx plus b. This is 1, this is 2. Okay, so in this equation, what is x? X is the state variable. What is u? U is the input variable. And what is y? Y is the output variable. What is transfer function? Ratio of Laplace transform of output to Laplace transform of input when all initial conditions are 0. So you have to take the Laplace transform of 1, assuming all initial conditions to be 0. Okay, taking Laplace transforms of 1, assuming 0 initial conditions. What do you get? Sx of s. Okay, actually, if you had not ignored the initial condition, you should have got x of s minus x of 0 initial condition. Okay, so since transfer function is defined only for 0 initial condition problems, x of 0 has to be 0. Okay, so sx of s equal to what? A into x of s plus b into u of s. Okay, So I can write this as Sx of s minus Ax of s equal to B u of s. Okay. So let me take x of s common. So what will this be? This will be as I. Okay. Why? Because A is a matrix, not a scalar. Okay. Capital A is a matrix, whereas small a is a scalar. Okay. If A was a scalar, then it would have been S minus A. Okay. Since A is a matrix, you have to consider the identity matrix. Si minus A into x of s will be equal to what? B u of s. Okay. So from this we get x of s as what? How will you find? You have to pre-multiply with Si minus A inverse. Okay. So you will get Si minus A inverse B u of s. Okay. Now you take, so this is equation 3. Now you take the Laplace transform of equation 2. So when you take the Laplace transform of equation 2, what will you get? Taking Laplace transform of 2. What would you get? Equation 2. Y of s equals C into X of s plus D into U of s. So instead of X of s, you put 3. Okay, substitute 3 into. 3 into. What would you get? Y of s is equal to C into Si minus A inverse B U of s plus D U of s. So I can take U common. So it becomes C into Si minus A inverse B plus D U of s. Okay, Y of s equal to C into Si minus A inverse B plus D U of s. So what's the transfer function? Transfer function is nothing but the ratio of Laplace transform of output to Laplace transform of input. What will you get? C into Si minus A inverse B plus D. Okay, so if you know your A matrix, B matrix, C and D matrices, then you can compute what is the equivalent transfer function using this thing, C into Si minus A inverse B plus D. Okay, now how will you find the Si minus A inverse? How will you find a matrix inverse? Adjoint divided by determinant. Determinant A. Okay, so that means this can be written as C into adjoint of Si minus A divided by determinant of Si minus A into B plus B. Okay. So we have seen, we have already discussed about poles. What are poles? Poles are the roots of the denominator of the transfer function. Okay. So here g of s is the transfer function. So poles of g of s will correspond to what? Will correspond to roots of determinant Si minus A. And what are the roots of determinant Si minus A? They are the eigenvalues. Okay. So poles of a transfer function. Poles of a transfer function correspond to eigenvalues of A matrix. Eigenvalues of A matrix. Okay, so determine Si minus A. So you can say that your determinant Si minus A is the characteristic equation, corresponds to the characteristic equation. Okay, so poles are given by roots of the characteristic equation, close to poles, right? Similarly, eigenvalues of this determinant Si minus A will give you the equivalent of the transfer function poles. Okay, let us try one example. Given x dot equals, one example, given x dot equals 0, 1, 0, 0, 0, 1, minus 1, minus 2, minus 3 into x plus 10, 0, 0 u. Okay, and y equals 1, 0, 0 x. Obtain the transfer function. Obtain the transfer function. Okay, how will you do? How will you obtain the transfer function? Transfer function g of s is nothing but what? C into Si minus A inverse B plus D. So here D is 0. Okay, so first we have to find what is Si minus A. So what will be Si minus A? A is a 3 by 3 matrix. So Si will be what? S0, 0, 0, S0, 0, 0, S. Okay, so Si minus A will be what? S minus 1, 0, 0, S minus 1, 1, 2, S plus 3. Okay, so what will be your Si minus A inverse? adjoint divided by determinant. Adjoint Si minus A divided by determinant Si minus A. Okay. So what do you get? When you do this, you should get something like this. S square plus 3s plus 2 minus 1 minus s plus 3 s into s plus 3 minus of 2s plus 1 s square whole divided by determinant Si minus A will be what? S cube plus 3s square plus 2s plus 1. Okay. So if you solve this, all this blah blah blah, finally you will get 10 into s square plus 3s plus 2 whole divided by s cube plus 3s square plus 2s plus 1. This is the transfer function. Okay. So we started with state space form ABCD matrices. Now we have landed up with the final transfer function. Okay. So G of s is equal to 10 into s square plus 3s plus 2 whole divided by s cube plus 3s square plus 2s plus 1. Fine. Now let us try another thing, another problem. Given x dot equals 0, 3, 1, 2, 8, 1, minus 10, minus 5, minus 2x plus 10, 0, 0 u. Okay, and y equals 1, 0, 0 x. Check for stability. Check for stability. Okay, so check for stability means what? You have to look for the eigenvalues of A matrix. Okay, so what is the condition for stability in the case of transfer function? All the closed loop poles must be in the left half of the S-plane. Similarly, if all the eigenvalues of the A matrix have negative real parts, system is stable. Okay, so first we have to find what is Si minus A. Okay, what is Si minus A? It will be S minus 3 minus 1 minus 2 S minus 8 minus 1 10 5 S plus 2. Okay, so eventually you can calculate what is determinant. Determinant Si minus A. What will be that? You will get S cube minus 6S square minus 7S minus 52. Now how will you check for the stability? You have to check whether all the roots are in the left half of the S-plane. Okay, straight away you can do, either you can factor this or straight away you can go for Routh-Hurwitz array, Routh-Hurwitz criterion. Routh-Hurwitz criterion. Okay, so highest power of S in the polynomial is 3. So our table should start from cube. Okay, so S cube, S square, S raised to 1, S raised to 0. What's the first row? 1 space minus 7. Next one is minus 6 space minus 52. Next one is minus 47 by 3 is 0. And the next element is minus 27. So you can see that there is one sign change from plus 1 to minus 6. Means what? One pole is in the right half of the S-plane and the remaining two are in the left half of the S-plane. Okay, so the system is unstable. System is unstable. Right? So that's all about state space representation. I urge you all to try some more extra questions. Okay, so if you have any doubts, just come back to me. I will stop here. Thank you.